Today we're going to talk about understanding Earth's climate and how it is changing. Conditionally, you should know that I'm a climate scientist, so that's the perspective I'll be sharing on this topic. The entire presentation's been broken down into sections, and I want to review those briefly so you'll know what to expect. I'm going to share some thoughts and perspectives on weather and climate in general, then talk about the disparity in climate change. A very important undercurrent whenever you deal with climate change is that it's moving at a different pace around the Earth's surface. Thirdly, we'll talk about some regional climate features that are changing in the Western Great Lakes region of the country. Then we'll talk about the consequences of those changes that are already being measured. And lastly, we'll talk about extremes, which after all have the most and greatest impact on our society. Weather is the condition of the Earth's atmosphere at the moment. It is commonly described by attributes such as temperature, precipitation, cloud cover, wind direction, and a number of other features. It is used in the science of meteorology to take the current measurements and frame them in a model context so that we can know what tomorrow's weather might be or next week's weather might be. Climate is more of a composite view of the environment around us. It is indeed the same attributes that we talk about in weather, but it's describing the climate or the behavior over a period of time and across geographic differences. The other real important feature with climate is to note that it is the end result of the interaction between the atmospheric attributes and the Earth's surface attributes. That's what gives us the climate, the long-term averages and the seasonal patterns and things of that nature. That's very important to understand the distinction between those two. Another important perspective on weather and climate is that the Earth's climate, Earth is 4.5 billion years old. The Earth's climate has been in a continual state of evolution. It's been forever affected by a number of drivers. It's affected by the sun and long-term variations in solar radiation from the sun. It's affected by changing Earth features, waxing and waning of ice cover, for example. Also changing ocean circulation patterns. It's occasionally massively disrupted by, for example, we all know about asteroid impacts that have occurred in Earth's history and impacted, for example, the demise of the dinosaurs and things like that. And so our entire history of the planet really suggests a story of an ever-changing climate relative to the planet Earth. That climate behavior that we now so emphatically measure with all our modern technology and instrumentation has been driven over time by categorically three drivers. One is the natural drivers, which I just alluded to, which is the geometry of the Earth and Sun relationship, occasional asteroid impact, ocean currents, etc. Two other drivers of Earth climate behavior, though, are tied to the human race. And those are changes that have been made to the Earth's landscape, such as, for example, commonly urbanization of an area where we've changed the configuration of the Earth's surface by urbanizing it and putting a built environment on the Earth's surface, if you will. Another is the extraction of resources from planet Earth in areas where we've done a lot of mining, deforestation, taking out wetlands, transforming landscapes to a managed agricultural setting, a number of other features. And that affects the interaction with the overlying atmosphere. So in reality, then you get a change in the climate attributes. And then that third category is, of course, the one most commonly talked about in the modern era, which is the changing composition of the Earth's atmosphere, driven dominantly by what we put into the Earth's atmosphere, the emissions that we produce in our industrial society. So the final word on this is that the Earth's climate and its behavior is driven by all three of these categories, and in composite they all have some measurable impact on the Earth's climate behavior. Our perspective of this behavior is also relevant in the context of understanding how we perceive this behavior. Across the last couple of centuries, climate scientists have perceived Earth's climate behavior with four distinct perspectives. This first one here that we call the stationary perspective dates all the way back to the founding fathers of our country, in that it is fundamentally based on measuring climate attributes such as temperature and precipitation, for example, at a point on the Earth's surface, day by day, year by year, over a period of time. And then after we build up a sufficient period of time, we can describe that climate's central tendencies, its means, its mode, values, etc., its seasonal variation, and its extremes. So Thomas Jefferson, for example, George Washington, Benjamin Franklin, many other founding fathers believed distinctly in this perception of climate behavior. There's also areas of the world where there's a strong perception of cyclical climate behavior, although that is mostly in the equatorial regions of the Earth's surface, which are dominated by cyclical behavior with the changing of the sun angle and the seasonal changes. And in fact, there is substantial statistical evidence that says that in those regions we do have distinct hot and cold periods, distinct wet and dry seasons, and things of that nature. We don't talk about the cyclical perception of climate behavior much in our region of the USA because, quite frankly, we don't see it. We don't see it play out here. A third perception of climate behavior, which is more of a 20th century perception, is that climate behaves over periods of time with changes or phase changes, if you will, in variability. This is kind of a modification of the earlier stationary view of climate behavior, in that it recognizes that over time, the variability around the central tendencies of climate waxes and wanes. Simply stated, we go through periods where it appears like the climate is stuck in a rut, and one year is like the next, like the next, like the next. And we also go through periods where climate behavior is highly erratic. One year is distinctly different than another. And so we have this amplified variability playing out in the climate behavior. And then lastly, and more relevant to this presentation, is the trend shift view of climate behavior, which argues the point, and very effectively, that if the climate is disturbed, for example, we continue to put greater emissions into the Earth's atmosphere, we continue to disturb the Earth's surface in terms of development and exploitation of resources, that we will alter the climate in terms of its interaction between the Earth's surface and the atmosphere. And in the end, what we'll do, graphically depicted here, is that we'll change the central tendencies in some meaningful way, and we'll also change the extremes in variability. And suddenly the measurements that we derive from the same point on Earth will start to look different than what the previous history has looked like. There will be behavioral changes outside the realm of what the history at that point on Earth has shown. So that's the trend shift perspective. 3 reasons to believe and hang our hat on the notion that the climate of planet Earth is indeed changing. I think these are important reasons. Certainly those of us engaged in climate science strongly believe in these reasons. The first is that the measured attributes, the temperature, precipitation, wind, solar radiation, etc., in 3 independently derived global data sets all show measures of change. Not only do they all show measures of change, we know that these changes are not random. These, in scientific terms, are statistically significant changes. Secondly, the models we use to mimic the Earth's climate system all fit the measured data, especially over the last 100 to 150 years, if we incorporate in those models the changes brought to the landscape by the human race, the changes brought to the composition of the Earth's atmosphere by the human race. And when we incorporate those, we know our models fit the measured parameters of the Earth climate system much better. And thirdly, the observed and measured physical and biological consequences that are increasingly being documented in recent years fit the measured changes in the climate attributes. So we know that the changes that have already occurred in climate behavior and, for example, precipitation behavior are already being played out in showing consequences to local landscapes and local behavior of weather systems.